In this lesson, we're going to have a look at the derivatives of exponential functions. Now, we're just going to do a little bit of exploring first. Now, this is what I want to happen. This is the goal. We're going to have an exponential function, let's say a to the x. I know that's the form of an exponential function. I want to differentiate this function, and I would like to know the derivative of the function. I want it to equal the original function. So what number base can I have? Is it going to be 2 to the x or 3 to the x, such that when I differentiate it, the derivative is going to be the exact same as my original function. And so I'm going to do that with a little bit of assistance from a technology. Really all I'm doing here is I'm plugging in, I'm saying, okay, I've got the function 1.5 to the power of x. I'm getting the computer to spit out what the derivative is going to be. And so we can see if it's 1.5, it's not quite. If we bump that number up to 2 to the power of x, well, we can see that the derivative is still underestimating. So I want to make that base number a little bit larger. If I make it 2.5, I can see that the derivative is getting a lot closer to the original function. That's what I want to happen. So I'm getting hotter here. And if I say, if I've got fx equal to 3 to the power of x and the derivative has overshot, so I know that, well, this base number, it's got to be between the range of 2.5 to 3. Okay, so I might try a 2.75 to the power of x, and I'm seeing it slightly overshooting. If I go 2.7 to the power of x, not quite there, but there's a special number called e. E as that base number, the derivative is equal to itself. Okay, and so that's just a little bit of exploring through using a derivative calculator, but we're going to have a look at why exactly that's the case. Okay, and so there's two questions. One, what is e and how do we get it? And two is, why exactly is it that if we've got a function that's an exponential, why is it that the derivative is an exponential? And so I'm going to start off by answering the latter first. Let's just consider we've got f of x equal to the power of x. Now, if we don't remember the relationship between a function and its derivative function, is that if you've got a function, the value of this slope tells you the corresponding y values of the derivative function. And so if you take a look at the gradient values of an exponential function, the gradient shoots up exponentially. So that would imply that the derivative function is an exponential. Okay, so we can see that here where I've got my m values there, and you can pause the video at any point and you'll see that the m value on my original function is equal to the y value on the derivative. And so that kind of answers why. It gives us a little bit of an intuition as to, we've got an exponential function, and if we're going to differentiate the exponential function, that derivative function is an exponential. Where did this number e come from? We're going to whiteboard here for a moment, and let's check it out. Where did this number e exactly come from? And so we're just going to play a little game here. Where did e come from? Well, let's say I've got a function f of x being equal to a to the power of x, some base to the power of x, and what I would like to happen is that the derivative of this function is a to the x. That's what I want to happen. So really the question is, what value for a is going to satisfy this? Okay, and it is it's a question that we've got to answer. So the way in which I would calculate a derivative is I would use first principles. So I say f prime of x and so here, well, I'm going to set this up using the definition of a derivative. And what we notice is with the f of x plus h term, you get a of x plus h in the power. If you do the reverse of our first index law, what you actually get is a to the power of x times by a to the power of h. And that's actually going to come in handy when we're trying to manipulate this guy here. So the derivative f prime of x, I want that to be a of x, and that's going to be equal to the limit as h approaches 0 of f of x plus h, which is a to the x times by a to the h, subtract f of x, that is a to the h, all divided by h there. And then here comes the question, what's the value of a that satisfies this? And so there's a little bit of a manipulation that's going to go along here, right? What I'm going to do here is I'm going to spot that I can factor out n a to the power of x on both the top. Okay, which is very nice here. And then what I'm going to do at this stage here is I'm actually going to divide both sides by a to the power of x. Because I want to get the a terms onto one side. So I'm going to do that, and when I divide a to the power of x by a to the power of x, I'm just going to get 1, and that's going to equal the limit as h approaches 0 of a to the power of x to the power of x, and I'm going to write that as a fraction, just a to the power of x over 1, so I can do some cross multiplying here. And what you'll notice is those a to the power of x's cancel off, which is kind of nice, and that leaves us with 1 being equal to the limit as h approaches 0 of a to the power of h minus 1 all divided by h. And so then the question is, well, as we take h to this limit, what power of a is going to give us this being equal to 1? Now, again, this is kind of a hard question to answer, so I'm just going to continue to manipulate this guy here. Right, what I'm going to do is I'm going to forget about the limit for the time being, and I'm going to evaluate it at the end. And I'm just going to manipulate this to try and get a by itself, because if I can get a equal to something, then I can find out what a is going to be. So if I multiply both sides by h here, I get h being equal to a to the power of h minus 1, bring that 1 over, divide, take the h root of it, and I get an answer for what a is. Now remember though, I am evaluating this for the limit as h approaches 0, so I say, therefore, a is equal to the limit as h approaches 0 of this stuff here, h plus 1 to the power of 1 over h. And I can do a little bit of cheating here by just using some programming to plug in some values of h. And what we notice here is that as we plug in smaller and smaller values of h, we get that this value of a is going to get closer and closer to the value of 2.718 blah blah blah, which is e. So this is where this number e comes from, right? And it leads us with a nice little conclusion. And really, if you're going to apply this to some problems, this last bit is all you're going to really need to have a look at, is that you say if you've got a function e to the x, where e is our base number, then what that implies is that the derivative of the function is equal to e to the x. And that is the nice part about this number, e. Okay, it's a special number. It's an irrational number, but it's pretty nice for differentiating exponential functions. Okay, so we're going to have a look at a few examples really quickly. Differentiating. So this first part here, I'm just calling this 0.5 because I think you need to be able to do these first two in order to really apply it. So if we've got e to the x, that means that the derivative is equal to e to the x. There you'd be done, right? And the derivative of, if you've got a scalar term in front of this, e to the x, so just a constant term, where it's multiplying here, it is still going to be the same thing, okay? So, and that's the nice part about having the base number e, because it allows this property for the derivative to be equal to the original function, which is very nice. Differentiate e to the power of 2x, okay? Here, what we're going to need to do is we're going to need to apply the chain rule here. So I've got e to the power of 2x, and I'm going to let u equal 2x. And I can apply the chain rule here, which is dy du times by du dx. I'm going to move that. Okay, so if I let u equal 2x, then I've got y being equal to e to the power of u. I can differentiate u with respect to x. The derivative of 2x is just 2. And I can differentiate this now, y with respect to u. E to the power of u, the derivative of that is just e to the power of u. Therefore, the derivative here is these two multiplied together. So I'd say it's 2e to the u, which is 2e to the 2x, because u is 2x. What you can do here is, when you're doing these, I guess, fast motion, if you've got e to the power of 2x, what you notice is you've got that 2x in the power. So if you want to take the derivative here, you look at what's in the power. I'm going to differentiate what's in the power, which would be the derivative of 2x is 2, so that comes down, and everything else stays the same. Let's look at another one. So I've got here, differentiate negative 2e to the power of 3x squared. No different, I'm just going to utilize the chain rule. So I've got negative 2e to the 3x squared. I'm going to let u equal the stuff in the power. And I can differentiate that with respect to x. I know that's just going to be 6x. And where y is negative 2e to the u, the derivative of that with respect to u is just itself, negative 2e to the u. Therefore, the derivative of this function is equal to 6x times by negative 2e to the power of u. Bring that negative 6 and the 6 and the negative 2 turn together, you get negative 12x e to the power of, where u was, 3x squared. So where these guys came together to make that, and this guy here is our u, which came from there. Okay, again, alternatively, if you're getting pretty fast at this, you'd say you've got negative 2e to the power of 3x squared, you would go, this stuff is in the power, therefore I'm going to take the derivative of the stuff in the power, 3x squared, the derivative of that is 6x. Bring down the 6x, times that by negative 2, you get negative 12x e to the power of 3x squared, and you'd be done.